Welcome to Mindset Detector EDS Basic Presentation. In this presentation, we will introduce you to the main idea of an EDS system. Mindset Detector has been developed by Decision Makers, and it is provided as an online and offline service based on cloud infrastructure. Today, we will discuss several matters. What differs SCADA from an EDS system? Detectors, the beating heart of the EDS system. What the system learns and how. Event classification, the system's human factor. How can a model quality improve over time? Cloud-based system. Why? What is Blue's contribution? First, let's review the events that took place on the 14th of August 2003 at the Midwestern United States and the Canadian province of Ontario. On that day, at 4:10 p.m., widespread power outage occurred due to a software bug at the alarm system set at a control room of the First Energy Corporation. A lack of alarm left operators unaware of a race condition in the control software. Early signs of a problem appeared about 3 hours before the disaster. Numerous monitoring stations went out of order within several hours before the blackout started. System operators were unaware of the malfunction. The failure deprived them of both audio and visual alerts for important changes in the system state. What would have been a manageable local blackout cascaded into massive widespread distress on the electric grid. Over 98 million people were left without electricity, communication, transportation, and water supply for over 7 hours. With the help of the Mindset Detector, on the occurrence of abnormal events, signals of an unusual behavior are observed long before the event takes place. On most cases, it is possible to activate statistical rules in order to identify anomalous phenomena much prior to the system's crisis point. The central complication is to recognize the abnormal situations which are a sign of a real malfunction out of those which are false alarms. Here are 10 things the EDS system can do on its own and SCADA can't. 1. Self-auto-learning of the statistical borders. 2. Recognize anomalous leaps that don't violate the low and high user limits. 3. Violating engineering rules. 4. Detection of long-term patterns before those become critical and calculate the time to alarm. 5. Detection of low-quality data, such as static parameters, unlikely time periods, and fixed noise. 6. Unordinary behavior of the I/O cards. 7. Detection of abnormal event combination. 8. Detection of event combinations previously defined as dangerous and calculation their approximate time of occurrence. 9. Unreasonable noise distinction in the system. 10. Detection of unexplained variance between different monitoring stations. Let's focus on 3 illustrative examples. 1. Fixed value for an improbable time period. 2. Unexplained leaps within the defined user limits. And 3. Rare combination implying an existing problem. Example number 1. In the following slide, we see data from 2 different sensors. The upper one has substantial amount of noise, and as you can see, there are almost none 2 consecutive records with identical values. On the lower part of the slide, you can see data from a sensor in which during a substantial amount of time, the data is fixed. Given the nature of water flow properties, it is most unlikely to see 2 consecutive records with identical values. Even less than that, several consecutive records with identical values. When this happens, it might be a sensor problem, communication problem, or improper sampling of the water. One of the things the EDS builds automatically for each sensor in the background is the histogram, which describes the frequency of fixed value events by their length. For example, the left side figure, where the horizontal axis depicts minutes and the vertical axis depicts frequencies, shows that around 70% of the time there's a difference between two consecutive records, and around 15 minutes, on the right side of the histogram, is the longest event of fixed data. Thus, an event in which a sensor transmits fixed data for more than 30 minutes is abnormal and must be investigated. How the fixed value detector is implemented in the EDS software. Very easy. All you need to do is define the delay before trigger time, the notification policy, and the base severity. The rest is done by the software. In case you're setting a new model, the Create All Detectors button will create all the necessary detectors with their default values. Example number 2. Another feature of the EDS is its ability to detect abnormal changes within the regulatory limits. In the current slide, measurements of 1 week of free chlorine are shown. The lower part of the slide shows the distribution of change for a time window of 30 minutes and 180 minutes. As you can see, a change of more than 0.15 plus or 0.16 minus is rare. On the 180 minutes window, these values are wider and range between 0.2 plus and minus. The EDS builds automatically these histograms internally for each sensor, and when a change in the sensor which is out of the relevant histogram occurs, an event is triggered. How this is implemented in the software. All you should do is click the variable rate of change detector type and select variable under detector key. Set the delay time notification policy and base severity as in the previous case, and define the rate of change specific parameters. Once done, the detector is ready to start its mission. Example number 3. A continuous process which runs in the background of every monitoring station builds the common and rare combinations table. The current slide shows the results of this process both graphically and in a table form. The upper left side of the slide shows that conductivity between 450 to 500 and pH between 7.4 to 7.7 are the most common combinations. All other combinations are rare. The table on the lower part of the slide shows that out of more than 1 million records, each record represents 1 minute sampling, 136,000 minutes measurements were turbidity 0.07, pH 7.4, redox 723, and conductivity 425. The table shows also other less frequent combinations until the most rare ones, which are at the bottom part of the table. The frequency table is used for online monitoring of data. The process produces 3 lines. The similarity line, the red one, shows how common is the combination at each time point. The distance line, the blue line, shows how far is each point from the nearest most common combination. The topology line, the green line, gives indication in the range of 0 to 1 about quality of the water given engineering knowledge. As can be seen from the above picture, during a quality event, similarity goes down, the red line, and distance to known combination goes up, and topology goes down. These are 3 indications that something is happening. Next, we will discuss event monitoring and management. When one of the detectors fires an alarm, an event starts to roll out. A dedicated screen in the system enables to follow which detectors are alarming and the status of the alarm. When the delay time is over and the event is still alive, a proper message is delivered to the monitoring staff. Event classification. Once an event ends, It should be classified by a human expert. Classification may fall into one of the four categories as follows. False, meaning the detector's wrongly identified situation as an event. True, the detector's triggered alarm which should get an attention by human staff. Ignore. Event is known to be caused by non-relevant circumstances, e.g. replacement of sensor. Other. Event is known to be caused by circumstances that should be manageable, e.g. maintenance. User may also add free description to the event. Over time, detectors that were triggering true events are getting good points. Detectors that were triggering false alarms are getting bad points. Detectors with bad points should be tuned. When an event is triggered by detectors with good points, the event should get immediate attention. The following gives high view of the system's architecture using a block diagram. A cloud-based server is hosting 4 different software components: the EDS system, the MS SQL server, the field device manager, and the web interface. The field device manager communicates with devices located on the ground, collecting water data online. Communication is based on SSL over GSM. The web interface enables users with proper credentials to approach the system from any browser-based connection. No installation of any software is needed. The EDS and the MS SQL are working in the background and can be accessed only by the system engineers. The entire system is located on a cloud server. A single system can handle hundreds of monitoring stations. The EDS has full internet-based interface which enables users, after short training, to use the system effectively. The unit's locations and status are presented on top of the geographic map based on Google Maps services. Dedicated control board enables to set up each one of the units and report about calibration activities. Graph and table-based view enable to visualize data easily. Set of ready-made reports enable to download data to the use of local machine. The back office of the EDS system includes an extensive engineering interface which enables to construct, tune, and maintain all EDS models. For details about the construction and maintenance on EDS models, please refer to the EDS set of presentations. Decision Makers' business model is based on offering its services as cloud-based service. No need to invest in an expensive computer hardware. Calibration and maintenance of models are included in the service. Alarms are automatically transmitted to the relevant engineers using email and text messages. Secured access enables users to monitor the system from any browser. Assuming that the customer is transmitting data from a calibrated field device, all is left is to set, tune, and go. Thank you for listening.